When you train a very long context model, the weights are only half the memory story. The other half is activations, the intermediate values every layer produces on the forward pass and has to keep around for the backward pass. For a long sequence, those activations can quietly balloon until they swamp the GPU, and no amount of splitting the weights alone will save you. Sequence parallelism, from a Megatron team in 2022, is a targeted fix for exactly that. Today, we're looking at how it shards along the token dimension to tame that activation memory, and why it pairs so naturally with the tensor parallelism you may already be using. Let's follow how the work actually gets divided inside a single transformer layer. Picture the sequence of tokens laid out in a row. Sequence parallelism cuts that row into pieces and hands each device just a portion of the tokens to hold and process, rather than the whole thing. Some operations are perfectly happy working on those separate token slices. Layer normalization, dropout, and the residual additions act on each token on its own, so every device can run them over its own shard with no coordination at all. The matrix multiplications are different. Those tensor parallel operations need the full picture across the hidden dimension. So right before them, the devices gather their token shards back together, run the heavy matmals, and then scatter the result back in a shard for the cheap operations that follow. The payoff lands on the memory-heavy, non-matmal parts, because layer norm, dropout, and residuals were exactly the pieces tensor parallelism left fully replicated. Sharding them across devices slashes the activation memory that used to dominate. So here is the shift in one clean comparison. Tensor parallelism on its own splits the big matrix multiplies across devices, but leaves the layer norm, dropout, and residual activations fully replicated on every card. For a long sequence, those replicated activations become the memory bottleneck. Add sequence parallelism, and you shard the token dimension for exactly those replicated pieces. Nothing is copied everywhere anymore. So the activation memory drops sharply, and you finally have room to train on much longer sequences. Now, 3 ideas really capture why this technique matters so much. Sharding along the sequence dimension means each device owns only a slice of the tokens, instead of copying the full activation set onto every card. Targeting activation memory is the whole point. It goes straight after the layer norm, dropout, and residual values that other parallelism schemes leave replicated and bloated. Pairing it with tensor parallelism is the intended recipe. Tensor parallelism handles the big matmals. Sequence parallelism handles the pieces left over, and together they cut activation memory enough to make training genuinely long context models practical on the hardware you already have. Okay, let's pull out the essentials. Sequence parallelism shards along the token dimension, so each device processes only part of the sequence. It targets the memory-heavy operations tensor parallelism leaves replicated, which are layer normalization, dropout, and residuals. Combined with tensor parallelism, it slashes activation memory and unlocks training on much longer sequences. In short, it splits the sequence itself, not just the weights, to fit long context into training. If you enjoy AI concepts made this clear, Standarity.com has plenty more waiting for you.